Now applying condition number 1 in equation 1. We get, now condition 1 is put x is equal to 0 in equation 1 and then substitute u of 0 comma t equal to 0. U of 0 comma t equal to a into cos 0 plus b into sin 0 into e to the power of minus c square p square t, and u of 0 comma t equal to 0. Therefore 0 is equal to a into cos 0, a into 1, sin 0 value 0, so therefore 0 into b 0 into e to the power of minus c square p square t. Since cos 0 equal to 1, sin 0 equal to 0. Now e to the power of minus c square p square t not equal to 0, as it is defined for all values of t. Even for t equal to 0 also, this is 1. It is not equal to 0. So therefore a equal to 0. This implies a equal to 0. Since e to the power of minus c square p square t not equal to 0, as it is defined for all values of t. It is defined for all values of t. It is not equal to 0. Therefore a equal to 0. Substituting a equal to 0 in equation number 1. The value of a in equation 1 we get 0 plus b sin px into e to the power of minus c square p square t. Therefore u of x comma t is equal to b sin px e to the power of minus c square p square t. Therefore u of x comma t is equal to b into sin px into e to the power of minus c square p square into t. Say this is equation number 2. Now applying condition number 2 in equation 2. U of L comma T equal to 0 for all T greater than 0. That means put X equal to L in equation 2. Now applying condition number 2 in equation 2. We get U of L comma T equal to B into sin PL, put X equal to L into e to the power of minus C square P square T. But U of L comma T is equal to 0 is equal to B into sin PL into e to the power of minus C square P square T. As explained in the previous case, e to the power of minus C square P square T not equal to 0, either B equal to 0 or sin PL equal to 0. This implies either B equal to 0 or sin PL equal to 0, since e to the power of minus C square P square T not equal to 0, it is defined for all values of T. So let us assume that B equal to 0 and then see what will happen. If B is equal to 0, B equal to 0, we already have A equal to 0. Then U of X comma T is equal to, now see, B sin PL e to the power of minus C square P square T. If B is equal to 0 here, 0 into sin px 0, e to the power of minus C square P square T is also 0. Therefore, 0 into finite value 0. Therefore, U of X comma T equal to 0. That means it is a trivial solution. That means there is no temperature in the rod at any time T and at any distance X. That means experiment has not been done. So that is a trivial solution. But here experiment is going on. So therefore we have to find the temperature distribution in the rod. So therefore B can never be equal to 0 to get the non-trivial solution. Then U of X comma T equal to 0. This is a trivial solution. A trivial solution. But we require non-trivial solution. For this, we have to assume that sin PL equal to 0. Therefore, sin PL equal to 0. Since B not equal to 0. B not equal to 0. We have seen that what happens if B equal to 0. Therefore, sin PL equal to 0. That means sin PL is equal to 0. Sin PL equal to sin n pi. That implies PL is equal to n pi. That implies P is equal to n pi by L, where n is an integer, L is a constant, length of the rod, pi, it is also a constant. Therefore, substituting the value of P in equation number 2. In equation number 2. We get now u of x comma t is equal to b into sin n pi x by L into e to the power minus c square p value n square pi square by L square into t. Therefore, u of x comma t b into sin n pi by L into x into e to the power of minus c square p square value n square pi square by L square into t. Say this is equation number 3. This is equation number 3. Since the given partial differential equation is linear, the linear combination of solutions of the form 3 with n is equal to 1, 2, 3 and so on is also a solution. This is called superposition principle. Since the partial differential equation is linear, the linear combination of solutions of the form 3 solutions of form 3 with n is equal to 1, 2, 3 and so on is also a solution of the equation. Therefore, the most general solution of equation 3 can be written as, this is called superposition principle. principle. The most general solution of equation 3 can be written as u of x comma t equal to sigma n is equal to 1 to infinity b suffix n sin n pi x by l into e to the power of minus c square n square pi square by l square into t. Say this is equation number 4. This is equation number 4, where n is equal to 1, 2, 3 and so on infinity, and bn is equal to b, capital B suffix n, n is equal to 1, 2 and so on infinity. So therefore instead of capital B we are writing small b for our convenience. Therefore this is the most general solution. Now we have to apply the condition number 3 in equation 4, that is initial condition, initial temperature in the rod, that is at time t equal to 0. Put t equal to 0 in equation number 4. Now applying condition 3, in equation 4, we get u of x comma t is equal to sigma n equal to 1 to infinity u of x comma 0 b suffix n into sin n pi x by l into e to the power of minus c square n square pi square by l square into 0, e to the power of 0, e to the power of 0 value 1. Now condition 3, we substituted t equal to 0. Now this value u of x comma 0 is equal to 100x by l for all 0 less than or equal to x less than or equal to l. Till now the solution is the same from equation number 1. Now the condition u of x comma 0 is changes. So solution also changes from here onwards. So the solution is the same as in the problem number 1 from equation number 1 to equation number 4. Just because of u of x comma 0 temperature distribution changes, from here onwards the solution also changes. This is 100 by L into x sigma n is equal to 1 to infinity bn sin n pi x by L e to the power of 0 value 1. Therefore, this is exactly the half range Fourier sine series expansion of the function f of x, where f of x is 100 by L into x. Therefore, we will find the value of bn by using the half range Fourier coefficient formula. We have by half range Fourier sine series bn is equal to 2 by L integral 0 to L f of x into sine n pi x by L dx. This is the formula. Here f of x is equal to 100x by L. Say this is a f of x. Therefore, bn equal to 2 by L integral 0 to L f of x 100 by L x into sine of n pi x by L into dx, multiplying 2 into 100, 200 by L into L, L square. So integrand is x into sine n pi x by L. Integration by parts by using Euler formula. Algebra first, trigonometry next. We will evaluate this integration by using the arrow marks method as we solved in the previous problems. Now derivative of x and integration of sin n pi x by L. Now derivative of x 1, derivative of 1 0. So we will continue the differentiation until the derivative is 0. Therefore integration. Now integration of sin n pi x by L. Integration of sin minus cos n pi x by L whole divided by n pi by L. Since coefficient of x is n pi by L, minus cos n pi x by L, derivative of sin is cos, by coefficient of x, that is n pi by L. This will comes in the denominator. Again, derivative of minus cos, that is minus derivative of cos is sin n pi x by L. Again, coefficient of x n pi by L. Already n pi by L is there here. So therefore n square pi square by L square. Now apply the arrow marks to multiply. Now x into this one minus cos n pi x by L by n pi by L, and 1 into minus sin n by x by L by n square pi square by L square, and again 0 into next integration, but 0 into any finite value is 0, so that's why I stopped the integration here only. So therefore now here alternatively plus and minus for these products, plus minus plus. So therefore first give plus sign, next give minus sign, after that give plus sign, and so on. Continue like this. Therefore now Bn is equal to 2 by L into integral 0 to L 100 by L x sin n by x by L dx. Therefore that is Bn equal to 200 by L square, 200 by L square into this one minus x into cos n pi x by L whole divided by n pi by L, again minus into minus plus sin n by x by L by n square pi square by L square, and limits 0 to L, plus sin n pi x by L by n square pi square by L square, limits 0 to L. Upper limit is L, lower limit is 0. Now substituting upper limit minus lower limit, it becomes upper limit L into cos n pi by L into L. L gets cancelled. Cos n pi value minus 1 whole to the power of n. Next lower limit 0 into cos 0, 0 into 1, that is 0. Next here upper limit sin n pi by L into L, L gets cancelled. Sin n pi value 0. Lower limit put x equal to 0 minus sin 0. Sin 0 value 0. For both upper limit and lower limit, this term becomes 0. Since sin n pi 0, sin 0 0. This is equal to 200 by L square into minus L into cos of n pi x by L into L, upper limit, plus minus into minus plus lower limit 0 into cos 0, 0, again plus upper limit sin n pi by here n pi by L, n pi by L. So now n pi by L into L minus lower limit sin 0 by n square pi square by L square. Therefore here LL gets cancelled. LL gets cancelled. Cos n pi value minus 1 whole to the power of n, but sin n pi value 0. So therefore here minus reciprocal n pi by L, reciprocal is L by n pi minus L square by n pi into cos n pi. L square gets a cancel. Therefore 200 into minus 1 whole to the power of n by n pi. This is equal to 200 by L square into minus L square by n pi cos n pi value minus 1 whole to the power of n. Since cos n pi minus 1 whole to the power of n, sin n pi 0, sin 0 also 0. Therefore now this is equal to L square gets cancelled here. Minus 1 whole to the power of n into minus 1. So that is minus 1 whole to the power of n plus 1 by n pi into 200. Therefore Bn is equal to 200 into minus 1 whole to the power of n plus 1 by n pi. This is the value of Bn. Now substituting the value of Bn in equation number 4, we get the solution for one-dimensional heat equation. Now substituting Bn in equation number 4. Now substituting the value of Bn in equation number 4, we get u of x comma t is equal to 200 is a constant, we are writing it out, sigma n is equal to 1 to infinity Bn value minus 1 whole to the power of n plus 1 by n pi, this is value Bn, into sine n pi x by L into e to the power of minus c square n square pi square by L square into t. This is a u of x comma t. This is the solution of our one-dimensional wave equation. Now problem number 2. A rod of length L has its ends capital A and capital B kept at 0 degrees centigrade and 120 degrees centigrade respectively until steady state conditions prevail. If the temperature at B is reduced to 0 degrees centigrade and kept so while that of A is maintained find the temperature distribution in the rod. Solution is same as in the problem number 1. So you can solve it. This is a homework. So this is a one-dimensional heat equation, problems related to one-dimensional heat equation.